Let me show you how to be a good Bayesian.
Hi everyone, welcome to this new Learn Bayes Stats webinar. Thank you so much for being so many people actually in the audience. We have a lot of people today to see you. Nathaniel, I am guessing this is not to see me because I've done other webinars before and some of those folks were not here. So, you know, causal inference would dictate that it is to see you indeed. Only my ego is bruised, but that's all good. So, how are we gonna do that, folks? So as I was saying, this is a Learning Bayesian Statistics webinar. If you don't know the show, well, you have a bunch of QR codes and links on the screen right now. If you want to follow the show, if you want to support the show, this is definitely something we do appreciate because that pays for the editing and all the background work that goes into each episode. And then you have some useful links also if you want to follow the show on Twitter, if you want to do some mentoring, consulting inquiries, online courses, you have all that here, and I will put that in the show notes or send me a message during the webinar after. Then I'm gonna pass the baton to Nathaniel. He's gonna take it from there. He's gonna go through the code, and of course we'll take a lot of questions. So please write your questions down in the chat. If you want, if it's a particularly complicated one, I think you can request to join the call, which I can do. So yeah, like lots of options, but basically that's all. And now I'm gonna shut up because for once, I'm not the one who's gonna talk the most, which is actually hard for me. And Nathaniel, I will stop sharing and you can take it from there.
Cool. Share my screen. This presentation. So I'm going to kind of start with a presentation just to kind of set the table a little bit with the sort of concepts that we are going to require throughout the sort of, as we walk through the notebook. It'll just be high-level slides, and then we'll dive into the code sort of directly afterwards. Alex, if you could keep an eye on the questions as they come through,
yeah.
Because the way I have my screen set up is I probably won't catch the questions as they're flying, if they're flying.
Yeah, I will interrupt you if there are some questions that need to be addressed live.
Okay, cool. So thanks folks for joining. We're going to be talking about non-parametric causal inference with PyMC. We'll cover broadly three topics: propensity score, propensity scores, debiased, machine learning, and causal mediation in a sort of escalating sequence of complexity. Some sort of background. I'm a data scientist. I work with Personio as a German startup. I work from Dublin. Sort of Bayesian statistician, open source contributor, and reformed philosopher. The pitch for this talk, very broadly, is that agnostic statistical methods in causal inference are well motivated but limited in scope. And we're going to try and show how Bayesian non-parametrics are a natural framework in which to couch and extend these methods. By agnostic statistics here, I mean broadly the statistics discussed in Aronow and Miller's beautiful little book called Foundations of Agnostic Statistics, which this talk owes a large debt to. It's a wonderfully concise book, which tries to articulate a framework for doing statistical inference with minimal assumptions. And that's not quite a red flag to a bull for a Bayesian, but it's certainly a spur to thinking. Exactly what we're doing when we're doing Bayesian statistics if people argue that they can get away with less. Another couple of sources that I think I wanted to call out that are sort of pivotal for this talk is the recent book Causal Inference in Python by Matthias Fakur, which is also a wonderful O'Reilly, very practical, hands-on introduction to causal inference in Python. And then thirdly, the Bayesian non-parametrics for causal inference and missing data by Daniels, Linero, and Roy is also a recent publication, and we draw a lot on it in the third and final section of the talk. I'm going to try and structure this talk to be sort of, it has 3 acts in a sense, like the initial act should be sort of setting the table, introducing the key terms, the concepts that we're going to use throughout. So talking about propensity scores, what they are, what the assumption of strong ignorability is, and how that is used to motivate the usage of propensity scores. We will then apply propensity score analysis in a successful case and a not so successful case. So that should be the sort of crisis, which will lead us into looking at methods to address the errors that can arise with miscalibrated propensity scores. And then we'll close. In a meme, something like this. Okay, so just a reminder of the obligatory Bayes formula here. You've seen it a million times, I'm sure, before. Traditionally, you're going to see it with this parameter theta. When we're talking about non-parametric Bayesian statistical inference, we sort of replace the parameter specifications with a sort of general stochastic process. So that can be methods such as the Gaussian processes, but in this talk and in the notebook that we'll walk through, we're primarily leveraging the BART Bayesian additive regression trees version of a statistical process for 2 reasons. One, there's a very nice package by MC BART, which I recommend you all check out. Secondly, BART as a methodology is quite close in spirit to random forest models, and that's wildly familiar in the broad machine learning and data science space. Cool. So 3 acts. We're going to talk about propensity scores and non-parametric inference, non-parametric causal inference generally. In the second act, we're going to talk about confounding issues with propensity scores and debiasing them. And in the third act, we'll talk about causal structure and mediation as a ways to rescue confounded inference. So we'll talk about, so skip ahead a bit, introducing the concepts that we need. So we're going to talk about potential outcomes as a framework for causal inference. So broadly, a potential outcome here is your outcome variable y under different treatment regimes. So this is the treated group or the control group, identified here as 0 or 1. Strong ignorability is an assumption that is going to be crucial for what we're talking about throughout. Strong ignorability states that the outcomes of the treatment assignment, conditional on a covariate profile X, this could be a big vector of attributes, are independent of the treatment. So that's Y0 and Y1 are independent of the treatment, conditional on the covariate profile X. The idea there is broadly, we want to be able to attribute the differences in the outcomes Y, so in our outcome variable Y, to the treatment, right? So when we're conditioning on X, it should be as, the membership in the treatment group should be as if random, conditional on the covariate profile X. The other constraint on propensity scores is that a propensity score needs to be between 0 and 1 for reasons that we'll get into. BART models, mentioned before, they're Bayesian additive regression trees. Non-parametric estimation is an important concept here, is that it's basically a model without a whole bunch of parameter specifications. In this case, we're going to be using BART because it reduces the amount of structural assumptions that you need to make in your model and reduces the risk of model misspecification by using these types of non-parametric models. Inverse propensity score weighting is the technique we're going to look into. Basically, we want to, I'll get into that more in the notebook. And we're also going to talk about doubly robust methods. Again, these are the formulas, but I'll get into it in the code. Okay, so go to code. Sorry, I know that was a lot of a preamble. I can go to code in 2 ways here, Alex. I can either go to the published notebook and walk through the published notebook, or I can go directly to my VS Code and we can step through a couple of lines.
Yeah, I think it's good if you have the live VS Code stuff or Jupyter, so that if you need to demonstrate some things or if people have questions, you can well demonstrate it live with all the risks that entail.
With all the risks that entail. Actually, okay, so let me. I might have to share my screen again. let's just share my window. Cool. You see my VS Code now? Give me a thumbs up, Alex.
Oh, sorry, I was muted, of course. Yes, we do.
Okay, good. All right.
And
okay,
I
cool.
think you can, get rid of the sidebar below and on the side so that we have just the code.
Yeah. Is that okay, screen?
Perfect.
Okay, cool. Yes, so this notebook is sort of very text heavy, maybe too text heavy, but I'm not going to try and read the text itself. Basically, what we want to do here in the initial section is just to introduce the notion of causal inference and propensity scores. The main use of propensity scores for causal inference comes with observed data rather than experimental data. So that's kind of found data rather than data that we have kind of arranged for the purposes of an experiment. And we want to evaluate the effect of a particular status in that observed data. So that could be the effect of being divorced on happiness. It could be the effect of smoking on weight gain, or the effect of smoking on health expenditure. In fact, those last two examples will be the ones that we are considering during the course of this notebook. We're using two distinct data sources. For the first data source, we're going to look at the relationship between smoking and weight loss. This is a data set that we have kind of robbed from the Miguel Hernan book, Causal Inference, What If? And which is also a book I recommend. And then the second data set on health expenditure data and their relationship to smoking, we have taken from the Linero and Roy book that I flagged at the beginning of the talk. So why do we care about propensity scores? Basically, the idea here is that we have observational data. We can't rerun the assignment mechanism to ensure that we have nicely allocated groups to the treatment status and the control status to cleanly evaluate the causal effect of that treatment status. But we can try to model the propensity for an individual to adopt a particular treatment status. And by using that propensity for treatment, we can reweight or adjust their representation in the treatment group or in the control group to then recalculate our treatment effect of interest. So that could be the average treatment effect, that could be the natural indirect effect, or the natural direct effect, as we'll see below. Just maybe, is that a clear definition, Alex? Have I given it? Is there any questions coming through? Okay, good.
Yeah, so it's clear to me, and I don't see any questions for now in the chat, so you can continue.
Cool. Okay. So that's what we hope to use propensity scores for. Causal inference more generally here, as I flagged in the introduction, is dependent on making this assumption of non-confoundedness, or strong ignorability, which is the claim that the treatment assignment is effectively random when we condition on the covariate profile in our data set. So, okay, I'm going to skip ahead here a little bit. This is what, if we're trying to depict this in a causal graph type structure, this is a relatively simplistic version of what we're trying to do. We're introducing this variable of a propensity score, so propensity conditional on X, which kind of blocks the path of the X variable. So this is your covariate profile to the treatment. And this is important largely because if this structural graph or this DAG is true in this sort of Judea-Pearl type sense, it means that the treatment is independent of X conditional on the propensity score. So strong ignorability, that assumption can go forward conditional on the propensity score as a scalar rather than conditional on the entire covariate profile X, which could be a matrix of the individual attributes. Okay, so individual attributes and covariate profile. So in this data set, this is what it looks like here, where we have captured for each individual in the data set attributes like their age, their sex, what their smoking intensity was, how many smoking years they had, a pre-treatment measure of their weight. So in this case, this is their weight in 1971, I think. Flags on like their educational status, their activity status, squared versions of the variables you've just seen. And the treatment effect here is whether or not they have adopted smoking post 1971. And the outcome is their weight as measured. Did I write it down here? Oh, I didn't write the year. It's a year post 1971, which I can look up and flag to you later. But yeah, so the idea here is then to measure the effect of adopting smoking on your weight, conditional on these covariate profiles. So we do some exploratory analysis here. We take the raw difference conditional on the treatment status. So that is whether or not the individual is a smoker at the time. And the treated difference here, the raw difference here is 2.5 pounds, I think, or maybe stone. But yeah, and then if we look at the same sort of split, again, we're looking at the difference here. So what we're doing here is looking at a particular strata of the data set. So this is like a kind of like the covariate profile we've discussed, but it's not the full covariate profile available in the data set, but it should give a sense of how the outcome metric varies conditional on different strata of our population. So like we're looking here at the population that didn't begin to smoke in the period, split by gender, race, activity, education. We're looking at their outcome, the average outcome for this strata of the population. We're looking at the global average of the weight loss or gain. So the global average was a weight gain of 2.6. For this strata, it was a weight gain of 2.8, and the difference between these two things. The reason we're doing this is we just kind of want to see, conditional on this sort of the specific covariate structure for these types of individuals, how does that change the implied difference due in part to smoking? We tried to plot these strata here as well to sort of make the pattern a little bit clearer. So you can see a couple of things here. So the sample size governs the size of these bubbles or points. The control group is the non-smokers, and the treatment group is the smokers. So you can kind of see a fairly broad pattern of the smokers are off to the right. They have smaller sample size than the non-smokers, which seems like a relatively consistent pattern across all the strata in our data set. But we might be a little bit concerned that our sample data is overrepresented with non-smokers, because each bubble on the non-smoker side has many more people in it than the smokers do. And so yes, again, if you take the mean across the strata, you get a sort of different average difference of about 3.66. So yeah, so this kind of exercise just suggests that we might want to be careful when we look at simple contrasts on any sample data that is not from an experiment. So just some simple contrasts on observed data for deriving causal estimates might be skewed due to bias of the data generating conditions that drove different people to adopt different treatment statuses in our data set. So what we want to do is model the propensity score for each individual in our data set. So we're going to prepare the data here. We're going to make our X data set, the covariate profile, which we are going to use to predict a propensity score. So, or to model the propensity score. And the way we model a propensity score is we take those covariates and try to predict, given our data, whether or not that person is a smoker or not. And the probability of becoming smoker is our propensity score, in a sense. How do we do that? Oh, I should really have been running this code as we're going. I know I've been talking a lot, but let me just load our packages. I have this. We'll load the data. Raw difference here. Just getting to the part where we want to model it. Right? So Okay, we have our X data set here. And this is a model specification, or rather it's a function that allows for the specification of a couple of different models, propensity models. This is important because we are going to contrast propensity scores generated by a simple logistic regression model as specified in PyMC and a BART style model as specified with PyMC. So there's kind of like quargs here. You get to pass in your covariate profiles. You get to pass in the outcome variable, which is smoker yes, no, in this case. We have our mutable data objects in here, whether or not we're fitting a BART model. If we're not fitting a BART model, we fit a logistic regression with the inverse logit. And we have a Bernoulli outcome as our likelihood. So I'll just fit this here. Note, this is maybe worth calling out if people are trying to run the code themselves. In the background, I'm running on Python 3.11 with a 5.10, I think 5.10 PyMC version. And I've had to include this init quarg here for adapt diagonal to prevent divergences with this this spec. Just to people. Anyway, this is always the fun with Bayesian modeling. You have to wait for the sampler. But I hope you at least see the progress bar.
Yeah. And just as a general note for people who maybe are not used to run Bayesian models, don't mess up with this quark all the time, right? The initialization quark, and usually just use the default that PyMC is using, because PyMC is choosing the default for you. And so usually it does a better job. You don't have to choose the initialization algorithm usually, but here in this case, that's needed for some reason. But in general, you don't have to do that. And if you do that, you should know what you're doing, which Nathaniel knows what he's doing here. But otherwise, you don't need to tamper with that. And also, it's not a general way of handling divergences. So divergences are really one of the things you really, really do not want in a Bayesian model. There are techniques to handle them. Messing up with the initialization algorithm is not a generic one.
No, not ideal, but just in case people are following along and had an issue.
Yeah.
This is slightly slower this time. I guess it's because I'm running the video call as well.
You're sharing your screen also, so it's like takes more time.
Yeah. It normally takes about 1 minute and 30 seconds or so. So just but this
for
looks like
for the other ones, we'll see how it goes. Otherwise, you can just use the what's already in the cells, and maybe we don't need to run it. We'll see. Depends on how much time you need.
Yeah, I think so. I might run the next one as well, just because I spend a bit of time with these two models. So let me just hit run for this one too. So this is the same function I'm calling here, but instead of fitting a logit model, I'm fitting a BART model. Yeah. And I'm drawing more samples.
Yeah. And we have some questions anyways, so that's perfect. Nathaniel, the notebook, the example is already live on PyMC's website, right? If I remember correctly.
It is, yeah.
Okay, so I'll link to that in the chat. Someone is asking for the code example. In the meantime, another one from Jade or Jade. I'm French, so I will read that as Jade. How much is the improvement of using BART to compute the propensity score compared to logistic regression? Any downside of BART, like overfitting, etc.? I'm guessing you have something to say about that.
Yeah, so to a large degree, this notebook is exploring kind of that question precisely. So we will see stuff about overfitting below. Yes. So I think maybe we'll just address that when we get to it. But certainly that is a concern.
Yeah, definitely. And rest assured, Jad, we will talk about that in the rest of the notebook. Ben is also asking, while we're on the subject, can you help explain why we might be seeing divergences in this case? You want to take that one, Nathaniel, or should I?
Yes, so I'm pretty positive in this case, without the adapt thing, the divergences go away when you remove the squared terms in this data set. So I think it has to do with sort of collinearity style issues with the logistic regression fit. So for instance, you don't see those divergences either way with the BART model.
Yeah.
If that makes sense. Okay, cool.
Yeah,
so both of those models have fitted. The BART model often gives this warning. It's generally not the case that this is actually a problem. It's just the BART model has like almost one parameter per observation. So it has a ton of parameters. And generally it's pretty okay. So we're going to plot the forest plot of the first 20 or so individuals and their propensity scores. So you can see here for the individual 0, in this case, BART predicts a propensity score of around whatever that is, maybe 11, 12, maybe a bit more, 14. And then logistic regression is a bit tighter and lower. But they vary in interesting ways, but not a million miles from one another, which is kind of good to see. Okay, good. What I'm going to do now for both models, just so that we can plot sort of the expected values of the propensity scores for each of the individuals, is to take the posterior distribution of the propensity score and average over the chains and the draws for each individual for both the Logit model and the BART probit model. Okay, cool. And then what we'll do is, this is rather a large block of code, but we will just plot the distributions. So we're seeing three plots here for the two models, right? So we see the propensity scores distribution for the treatment group and the control group for both models, the BART model and the logistic regression model. I've also flagged extreme propensity scores at the barrier of 0.10 and I think 0.9 over here. And the reason I'm flagging these extreme propensity scores is because one of the conditions for a propensity score to be useful is that it be between 0 and 1, and a propensity score too close to 0 or too close to 1 practically means that you have sort of you will have perfectly predicted that individual in your sample. And that will prove to be a problem when we're seeking to use the propensity score as a sort of out-of-sample similarity metric between individuals to be used in our reweighting schemes. I want to try and give a bit more intuition about why that might be a problem for causal inference. So if you recall that we have this strong ignorability condition, which is that the treatment allocation should be effectively random, conditional on your feature matrix X. And if you have a model which overfits to the sample data and can perfectly predict allocation to the treatment status in your sample, that means for that covariate profile, the model thinks there's almost no chance of a well-defined causal contrast because it's going to predict 100% of the time, for instance, if this covariate profile is a smoker, it's going to predict 100% of time that this covariate profile is a smoker, which means conditional on that covariate profile, you can never have a well-defined contrast between the smokers and the non-smokers. That is what the model has learned from this sample, which makes it useless as an estimate of similarity in the out-of-sample world, in the population. I hope that kind of makes a little sense. So this is the same distribution here, but we've just pivoted over the treated group to the other side to see if we can show how the distributions come apart. And then at the bottom, this is just the outcome variable, so the weight loss variable, conditional on age at the bottom, and we have sized the bubbles, so sized the individuals by the extremity of their propensity score. So you might just see here that the largest propensity score is probably over here for someone who's very young but has very high weight gain in the period, for instance. Again, these are just exploratory kind of plotting devices. Okay, good. Alex, did you have a question?
No, I'm good. I don't see any questions in the chat either. So basically, if you go back, maybe to make sure people understand, if you go back to that point you showed, so that person young but big gain weight, so that's it's sized by the inverse propensity score, right? So then what does that mean for the model?
Well, it means that the model thought that this particular individual, is it red, so it's in this control group now, so has a kind of a very high propensity for treatment. So inverted, it's still the biggest. So a high propensity of treatment gets inverted, and then is still a big weight that we're going to use downstream in our reweighting schemes, so to speak. So this individual
it's because that person is relatively rare in the sample, and so then that means to not have an under representation of that type of person, to then be able to make causal inference and have that I don't remember the technical term you used at the beginning, but that basically balanced idea of control and treatment.
Yeah, so maybe it's worth saying something about that in general. So the idea of reweighting schemes, with inverse reweighting schemes, is we want to find people in the treatment group, so smokers. We've modeled them, so we find a measure of high probability of being a smoker. So it means that so someone, for instance, who has a 0.9 propensity score and is in the treatment group, so is a smoker, it means people who look like that person will already be very prevalent in the treatment group, right? So we want to downweight his contribution to the statistical summary that we are estimating. And instead, if people who have a low propensity to being a smoker, so maybe they're very healthy in all of their dimensions of their life, but they're still a smoker, the model will predict that they have a low propensity of being a smoker, and we want to up their weighting in the smoking group because they're like a rare profile effectively in that group. So it rebalances
a healthy
in that
smoker.
way. Exactly.
Healthy smoker, which is rare. So we want more of them in there. Yeah. It looks a lot like the reweighting they do in the polling industry.
Yeah, exactly. So like post-stratification weighting on like what's nice about that case is that they can just use population weights because they have, say, census, rather than we're using a model to derive a weight to reweight another kind of model. So we're kind of like two models deep before we get to our causal effect, so to speak.
Yeah, no, for sure. And post-stratification is super interesting. I have a podcast episode about that, one or two, I think. I will link to that in the chat. And I also teach that in my latest online course, which is going to be out, hopefully, in March. Advanced regression. I will link to that too. And we have two questions, Nathaniel, from Andrew. One, what are ways of dealing with extreme propensity scores? I think you can take that one pretty fast and easily. And second, is probability calibration relevant or necessary for propensity models?
So this is, yes. So the first one, right, there are certainly ways of dealing with extreme propensity scores. In the literature, mostly this is done with even cutting individuals completely from your data set, which have high propensity scores. The other way is to use propensity scores with a matching algorithm, and then you only match very well matched pairs, which is also effectively a kind of data removal operation. It's a bit hacky. I think you could argue, and I kind of do argue in the piece a little bit, that these extreme propensity scores, if you believe them to be so extreme and not reflective of the population, then you just have a miscalibrated model to begin with. And you should have a better model of the population propensity score that you're going to attribute to this individual, which you can do. You can use in a Bayesian setting by having sort of stronger priors to pull away from extreme propensities, for instance. That's one way of doing it. Is probability calibration relevant or necessary for propensity scores? Yes, it certainly is. We will talk about another way in which to achieve more realistic propensity scores using k-fold cross-validation below as well, which is also a type of indirect calibration to the population rather than to the sample. The entire risk with propensity scores is that you sort of over-index on the sample. But what you're trying to do is capture the sort of individual propensity at a population level. And you can kind of address that in a number of different ways, some more hacky than others. I think, yeah, okay, cool. So what we're doing next is, so if you recall, we said that conditional on the propensity score, we want the treatment status, conditional on the covariate profile, we want the treatment status to be effectively random. And one way of kind of looking at that or interrogating the plausibility of that assumption is to plot the balance of the covariate distributions conditional on the propensity scores in some sense, right? So what we're going to do here is take the logit propensity scores, cut them up into 5 quantiles, and sort of plot the density function of our covariates conditional in this way on the propensity score to try and evaluate balance across the treatment and control group for the covariate profiles. So this is kind of common enough in the literature for both inverse propensity weighting and matching. What we're doing here is, so basically I'm plotting as before, the control group is the non-smokers and the treated group is the smokers, and the overlap is colored purple. So the more purple you see here, the better the balance is in these plots in some sense or other. We also calculate the standardized mean difference in the ages represented in the control group and the treatment group conditional on these propensity scores. And we look at a bunch of different variables or covariates in our data set. So first we look at age. We can see reasonably well-balanced conditional on these propensity scores. Similarly for weight as measured in 1971. Standardized mean difference here is like 0.04, 0.02, 0.09. And you can kind of, like you can, I think in the literature they recommend some cutoff points where the standardized mean difference is deemed too high. To represent a fair notion of balance, which would be an indicator that your propensity scores are misfit or miscalibrated for the use that you want to use them for in inverse propensity weighting or indeed matching. And we do the same sort of plots for each of the different covariates. So broadly, in an ideal world, we would have perfect balance conditional on the perfect balance of the covariate profiles conditional on these propensity scores. But I think we have reasonable balance here with the logit model, which allows us to sort of proceed. Yeah, okay, so we now want to use these propensity scores in an inverse weighting scheme. And there are a number of different sort of different weighting schemes you can use that are recommended in the literature. One I'm calling the raw propensity scheme, the raw inverse weighting propensity scheme. The other I'm calling the robust inverse propensity scheme, and the other I'm calling the doubly robust. Sorry, these aren't my names exactly. These are in the literature, but they're all slight transformations of the propensity score used to reweight the presence of a covariate profile within the treatment group or in the control group, in the way that I discussed with Alex there about 10 minutes ago. The the main difference I want to point out here is, like, if we're just using the raw case, all we're doing here is for everyone who's a smoker, they get the propensity score. 1 over the propensity score is the weight, so inverse propensity score. Everyone who's a non-smoker gets 1 over 1 minus the propensity score. That's all the transformation is. You modify the outcome variable, so you multiply the outcome variable by that inverted propensity score, and then you will ultimately calculate the contrast that you're interested in, so the difference in outcome between the treated group and the control group. That is the general pattern. You take the propensity score, you transform your outcome variable, you calculate the causal contrast of interest. Doubly robust propensity score adjustment is an interesting special case. And so again, you have your propensity score model. You're trying to define a weight to which to use to reweight the outcome variable and measure causal contrast. But here you also allow for a direct model of the outcome variable. In this case, we're just using a simple OLS model to predict the outcome, which is weight loss, conditional on the covariates per each group, right? So within each group. And the doubly robust adjustment weighting scheme is effectively a compromise weight allocation between a model of the outcome, in our case, OLS, and the propensity score model itself. And these are the formulas used to sort of calculate those outcomes that you're going to use to define a causal contrast. I want to try and give some intuition why this model or why this compromise is important and interesting. So this formula here at the top, right? What I want you to imagine is that our model M1, which is our OLS model, is an absolutely perfect fit for the outcome variable. Gets it right 100% of the time. So then the numerator of this fraction is the difference between y and the perfect scoring model, which is 0. So this will collapse, and then the weighting we're going to get is basically an average of the model predictions. Right, so this part of the equation collapses. So we're taking the average over the model, right? And then, but if it's a misspecified model, then there's some gap, there's some error between these terms, right? So we're calling it epsilon in the numerator. But if the propensity score model is accurate, the presence here, then then in the treated class that we're looking at here, the denominator should be high, which is say around 0.9. And as such, the estimator adds a number, epsilon, back to the M1 prediction over here and informs the weighting scheme again, right? So why this is called doubly robust is that we only need one well-specified model to achieve sensible or plausible weights in our weighting scheme. If we have a perfect prediction model of the outcome, we get sound weights. If we have a good propensity score model, we also get sound weights. So it's kind of a hedging. If we can model one of these things well, the doubly robust estimator of propensity score weights will give us weights that we can use well in the estimation of causal contrasts. I know that was a lot. So if there's questions now, I think it is worthwhile working through some of the algebra on your own. It is a beautiful kind of idea, but I hope I've given some intuition around why that is kind of a nice and interesting contrast between an attempt to model the outcome and the attempt to model the propensity scores.
Yeah. And there is no question in the chat for now, but what I would have is, when would why would you not use the doubly robust method then? It seems to be the most soundproof, let's say.
I mean, I guess it's more just like more work to specify two models, and but like if time was unlimited and you had enough incentive, I think you should definitely have already a model of the outcome in your head and a model of the propensity. So you should kind of use those two. But it might be enough to just get away with fitting a logistic regression model, getting propensity scores that work reasonably well, and just going with the raw adjustment, for instance, right? And in the literature, but doubly robust methods are certainly advisable when you have reasonable models of both, which I think it's certainly reasonable to do. Okay, good. So now this is a large plotting block, so I'm going to skip ahead. But what we're doing now and what we're seeing here is a plot of the propensity scores at the top here by treatment group or treatment status. One treatment, the control group here, treatment groups here. This is the outcome, the raw outcome variable presented in the same fashion. And maybe it's a little hard to see here, but basically what I've written out here is the causal contrast as defined on the raw metric, the 2.5 that you kind of saw above. And then in the third plot, which you see here, is the weighted outcome metric presented in the same fashion with control on top and treatment below. And then I've defined the causal contrast for you based on the reweighted outcome variable. So what you see for the logistic regression propensity scores, the mean of the logistic regression propensity scores, is that a naive contrast would give you a causal effect of 2.5, and a reweighted contrast would give you an outcome of 3.4 weight gain. Okay, that is very close to the estimate reported in Miguel and Hernan's book, which I think is 3.47 off the top of my head. So this looks healthy. But I'm only plotting here the outcome and the reweighted outcomes conditional on the mean of the propensity score distribution, which as good Bayesians is sort of not enough. So the next coding block, what that does here is it's a bit clunky. It takes an index for a sample value of the posterior propensity distribution based on based on the model, either the Logit or the BART model. And then we loop through each of, say, 4,000 propensity scores, conditional on each model, and define these causal contrasts, these reweighted outcome variables, and the causal contrast of interest in this table. So each row in this table is the summaries that we saw conditional on a different sample from the posterior propensity distribution of the logistic regression model, or the BART model in this case, right? And then we plot these two things, right? So these are the sort of expected potential outcomes, and this is the average treatment effect derived from the full posterior propensity distribution. So and the average of the ATEs is 3.58. So does that make sense to everyone in chat, especially those who aren't familiar with maybe Bayesian posteriors?
Yeah, I mean, to me that makes sense, but I have reviewed the notebook and I'm familiar with Bayesian stats, so I am biased. But yeah, if you have any questions, feel free to ask them now. We have a question from Yasser. Can the doubly robust weighting be extended to assume possible nonlinearity? Can it also account for uncertainty, e.g. using Bayesian regression, rather than just point estimate from OLS? And also, can this easily also extend to Kate? So conditional average treatment effect.
Yeah, so there's a lot there. So I think what I just spoke to is maybe the last point there on the first comment is about this is not just point estimates. We can use these weighting schemes, the doubly robust and the robust ones, to process the posterior of a propensity score distribution and then output a sort of posterior distribution for the ATE in this case. Can the robust weighting be extended to possible non-linearities? So doubly robust weighting can take any model specification. Like your propensity score model can be a BART model, which will be able to handle non-linearities. It could be a Gaussian process model, which could handle non-linearities in the estimation of propensity scores. Similarly, in the doubly robust estimator, your outcome model, which here I've coded as just a simple OLS model, you could be much more sophisticated with how you specify the outcome model. So you could have a BART model, you could have a machine learning model, whatever it is, it just needs to spit out a prediction which gets balanced against the propensity score in this doubly robust estimator. So I think yes to all your answers. Can this easily be extended to Kate? We will talk about Kate below, not in extreme detail, but I will touch on it. So I might wait till we get to that section. Okay, so yeah, so basically this was the posterior distribution of the average treatment effect for the logit model. We show the same plots where I'm using the raw adjustment method here rather than the robust one that we saw above, but same type of plot for the BART model. Again, the raw contrast is unchanged, it's 2.5, but the adjusted or reweighted contrast on the expected value of the propensity scores for the BART model shows a 3.3 treatment effect, or average treatment effect, which is again broadly in line with what you saw with the logistic model. So all looks reasonably good here. I do the same exercise pulling out the average treatment effect conditional on the posterior of the propensity distribution attributed by the BART model to derive this plot, which gives you sort of an expected ATE of 3.44. So that all kind of makes sense. So getting to now maybe a discussion of like why we're interested in flexibility of sort of non-parametric BART models versus simpler logistic models, and what role the sort of flexibility of BART has to play in propensity score weighting, what are the risks of it, and what are the sort of appealing features of these very robust prediction models. So what I'm going to show here is a plot of the posterior predictive distribution for each model, for the logit model and for the BART model. Here in this case, we're predicting whether it's a smoker or not. So our posterior predictive distributions have these nice kind of binary shapes. And what we're going to do is we're going to go down sort of increasingly complex covariate profiles to see how the model responds to predicting narrower and narrower strata of our sample. So this kind of reveals a nice feature of flexible modeling. So like what you'll see here is as we go down the strata, so this is a race-specific posterior predictive distribution. This is a race and gender strata of the posterior predictive distribution. And this is race, gender, and whether or not they're active strata of the posterior predictive distribution for the logit model on the left and the BART model on the right. So what's nice about this plot is that it shows on the right that the BART model is still making very kind of healthy predictions at the outer edges of these strata of our sample, which means it is quite accurate at predicting whether or not this individual in this covariate profile becomes a smoker or not. That's a good thing in a certain sense. It's good because it shows that BART is a very flexible model that can capture accurate predictions at the sort of finer edges of our covariate profile. But it poses a risk for us when we're trying to use these BART models in inverse propensity weighting schemes, because too perfect an allocation risks like propensity scores close to 1 or close to 0, which prevents us from being able to define the causal contrasts of interest in our sample, which makes the estimate of the average treatment effect derived with an overly fit BART model very unstable and inaccurate. Okay, does that make sense? And I will show an example of where that breaks down in a minute. But I also want to just discuss how we can use propensity scores in simpler regression modeling. I'll breeze through this part because I want to touch on regression modeling now and come back to it a bit later. But basically, we can take a propensity score we can take our treatment effect, and we can try and predict the outcome variable y and gain a coefficient for the effect of the treatment with a simple regression model that you've probably seen a million times before. And with a well-calibrated propensity score, we can substitute this propensity score for the full set of x variables, right? We don't need the full covariate profile, because the propensity score has bundled up all that structure, and it plus the treatment variable will give us an accurate measure of the treatment effect, which is nice to see when it's well calibrated. So what you see here is a well calibrated propensity score model that recovers the treatment effect using simpler regression. Similar case with the BART model for this data set, 3.2 versus 3.4, not a million miles off. Okay, so that's one way of reading a regression model. But if we want to be sort of non-parametric about it, or non-parametric about reading our causal estimands from the linear structure of the regression model, we can adopt an approach sort of advocated by Aronow and Miller, where we use the regression model to impute the counterfactual potential outcome distributions and define our causal contrast across the imputed potential outcome distributions. And this is a pattern that we will see below in more complicated cases. So I'm introducing it now because in the regression case, it's relatively straightforward. So what we're doing now is we're taking the fitted model, the fitted PyMC model, and instead we've defined the propensity scores to be the mean of the probit propensity scores for each individual in the data set, and we are setting their treatment status to 1. And we will then push forward our posterior settings, so to speak, and sample from the posterior predictive distribution under these counterfactual conditions that everyone is in the treated group. We do the same exercise for when everyone is in the non-treated group. And so we have now 2 posterior predictive distributions for the treated and non-treated, for which we can define the averages, for instance. So this is the average outcome variable in the treated group, in the treated counterfactual group. And this is the average outcome variable in the non-treated counterfactual group. And then we can define a causal contrast, which is effectively another way to estimate the ATE, or average treatment effect, under these sort of imputed counterfactual scenarios, which is a 3.12, which again is not terrible, but not quite 3.4. The point of introducing that now is just because this type of imputation scheme is one that is kind of seeks to avoid overly interpreting the parameters of the model, and is kind of semi-parametric in its approach to estimate or understand the causal effect of different treatment regimes. Okay, so I think that a lot of that is I just kind of set the table there with a lot of concepts. I might jump back to my slides. That's all right. Do you still see my slides, or do I need to reshare? Oh, you don't. You don't. Okay, 1 second.
Yeah, you need to reshare. Yeah.
Okay. Again, less table to set, but so in the second half, I want to talk about how propensity scores can be miscalibrated, BART models and their overfitting risks, and how we can potentially use double ML or debiased ML approaches to address some of that risk. And we will also talk about Kate estimation. We'll talk very briefly about Kate estimation, but what's nice about this case is we can use the debiased ML approaches to sort of quickly and neatly derive estimates for the conditional average treatment effect. I'll talk very briefly about that when we get to it. Miscalibrated propensity scores. I think we've already talked about this. I wanted to sort of flag here that we've talked about this. Basically, by over-indexing on the sample, propensity scores can be too close to 1 or 0, which makes them less useful for the role we intend them to be in the weighted scheme. Overfitting is this plot here. K-fold cross-validation, I'll maybe just discuss when we get to the double ML section. And Kate estimation, just for those who don't know what a conditional average treatment effect is, and the challenges of estimating them. So basically, you want to just sort of look at the treatment effect. If you just look at the treatment effect between the two groups in a random control trial, you're just looking at the differences in the outcomes between the two groups. In a random control trial, if you want to look at the conditional average treatment effect, you do it for the strata that you're interested in, and then look at the causal contrast. For estimating the conditional average treatment effect in an observational case study, it's sometimes a bit trickier, and that's what we will sort of begin to address a little bit in the talk. Let me jump back to the code. Okay. Okay, so now you can see my VS Code again, right? Cool. Okay, so now we're going to look at a different data set, a data set around the sort of total expenditure on health costs in the US that could be attributed to smoking. We're going to primarily look at, so smoking is our treatment variable. We're primarily going to look at the outcome variable, which is the log total expenditure. So that's this outcome here, log y. And what's kind of interesting about this data set, as we'll see, is that it's hard to discern any sort of average treatment effect in the data. So to start with. So again, the causal contrast you saw before, total expenditure is 8 on the log scale here for both groups, right? 8.04 versus 8.09, sort of minimalist. We do the same exercise where we sort of stratify it out. We plot these things. Again, you can kind of see some imbalance in the treatment versus control group in terms of sample size. But it's kind of a bit all over the place. All the differences from the global mean are all quite close to 0. It's not clear whether blue is to the left or blue is to the right in each strata. It's kind of hard to see a clear pattern from the visual. I pulled out the stratified difference. It's also quite low. Some exploratory plots here to sort of give a sense of what the distributions look like. So recall that we're looking at the log total expenditure. So this is like now on a scale basically between 7 and 11. I want to highlight that because like a unit difference in change here is a huge change in this distribution, right? I'm flagging that ahead of time, foreshadowing. The quantiles, the empirical quantiles here seem very closely knit all the way up to maybe the very latter quantiles of the distribution. When you plot the outcome versus their log income and their age, sort of indiscernible across these two plots. We do a QQ plot here as well, same idea as the empirical quantiles, but like they match up almost perfectly until you get very, very tiny differences at the outer edges of the quantile, which is all to say that it's very hard to see in this population, in this data set of about 16,000 people, that there's any major average treatment effect that we will see in the data. What could go wrong? So what we're doing here is we're just going to take a sample of the data set and we're going to fit a propensity score model to it. Again, calling the same function you saw above. We fit both, but we're primarily concentrating on the BART model here. I'm not actually running any of this code. Should I be running this code? Let me just 1 minute 8. Let's just run this. So yeah, so but yeah, so what we want to kind of show here is that after our exploratory kind of data analysis, which sort of suggests minimal to negative impact of smoking on this total health expenditure, which might seem puzzling, we can fit a BART model which will recover another puzzling outcome. And I want to dive into a little bit why that is occurring. and how we can try to address that by getting better calibrated propensity scores in some sense or other. Just, yeah. Yeah, so this is, yeah, still going fast, but a bit slow. Not too bad.
Yeah, it's pretty good, especially considering you're sharing your screen.
Yeah. I think this Logit might be, it's chugging along nicely.
Mm-hmm. Yeah.
I might skip the trace plot because it will show similar to this, but it just takes a longer time to plot all these 1,000 parameters.
Oh yeah, that's going to be long.
Yeah. But I'll do
these
some
are
plots.
Healthy trace plots, let's say.
Yes, these are very healthy trace plots. Yeah.
Yeah.
Okay, did we finish that? And the posterior predictive. Yeah. Okay, 1 minute 32 seconds. Not too bad. Okay, good. So next, what we want to do is basically an analog of the plots you saw above. Just looking to see any indications of kind of unhealthiness in the propensity score, which, like, there's very little overlap here, which is a kind of indication of the violations of positivity. So lots close to 0 and some close to 1 over here, for instance. That's not decisive from that plot. But if we do this plot below here, the one where we try to calculate the contrast, we see something very striking. Again, this is the raw difference on the unweighted outcome variable. So this is log expenditure. We see like 0.00 as the raw difference. But in our reweighted outcome variable, we see a suggested treatment effect of 1.45. But this is on the log scale. So this is huge. This is a huge treatment effect that was not at all suggested by our exploratory data analysis. So it sort of suggests that something is going wrong. So we want to try to dig into this a little bit. So if we plot the robust and doubly robust average treatment effect distributions, so this is the robust one, we see a slightly healthier but also quite extreme expected average treatment effect of 0.44. And then if we do the doubly robust weighting scheme, we see a healthier but also still kind of high treatment effect of negative 0.16. So the signs are still negative, right, for both cases. So what's interesting here, I think, is to recall how the doubly robust weighting scheme tries to affect the compromise between a simple OLS model, in our case, and the propensity scores. And what's happening here is that the compromise weighting with the outcome fit is pulling it back to 0. Like, so that it's suggesting that the propensity score model is miscalibrated, and the OLS model, which is our model fit, is pulling it back towards 0, away from either 4.4 or, in worst case scenarios, 1.44, right? Which is cool to see, right? That's what the doubly robust estimator is supposed to be doing. We can also kind of do some due diligence and inspect balance plots for our covariate, so for BMI. And you can kind of see that this looks nowhere as healthy. There's not as much purple, for instance, as the balance plots that we saw above. Let's see, I'll just plot this if I can. Have I got everything? Yeah. We'll do another one. We'll do some live coding this time, where I try to just do age and see what that looks like, rather than. But there you go. So age is also sort of out of whack in some sense, right? So, and you can look at the differences here. Standardized mean difference is like negative 0.37, negative 2.6. So there are, like, in the literature, like statistical tests you could run on this sort of standardized mean difference conditional on the propensity score to give yourself a decision criteria, if you like that sort of thing. But I think the value that this kind of plotting does is more just like a visual sense check. Is everything in order, or do we need to worry? Again, so how does regression help? We can now sort of pull in regression models. Again, the pattern we saw before, where we're fitting a regression model with just the propensity score, because the propensity score is miscalibrated, our estimated treatment effect here is 1.2, which is also huge, right? So it's basically suggesting that with a miscalibrated propensity score, regression can't save us unless we pull in some more covariates. And then regression will do its magic and weight each of the covariates appropriately and try pull us back towards zero. So the treatment effect, when we've put in the measures of health outcomes and age and BMI, which should be more determinative in the causal story around health expenditure, allows us to pull our estimate of the treatment effect back towards zero. So how does regression help? Like I think Angrist and I have forget his second name. The authors of Mostly Harmless Econometrics, which is a lovely little book, have this nice quote which is saying that regression control for the right covariates does a reasonable job of eliminating selection effects. So what we were seeking to do with propensity score matching, like to reweight the data in such a way to remove the selection effects that were in the observed data, can also somewhat be automated if with a good regression model with the right covariates in it. It does it not quite by magic, but like regression is a weighting scheme in itself. There's no magic to finding what are the right covariate profiles to fit in your regression. That is the nature of the game. But it is worth knowing that a miscalibrated propensity score can be fixed or addressed in a regression setting. Any questions on that at the moment? Because we're about to move Pisky. Yeah, thank you.
Yeah. Yeah, thanks. No, I don't see any questions here. Some discussions about Book of Y, structural equation modeling, stuff like that. But no, we're all good. And yeah, thanks a lot, Nathaniel. I think this is going really well.
Okay, good. So we're about to move on to the section on debiased machine learning and the Frisch-Waugh-Lovall theorem. And most of this material I've taken pretty much wholesale from Matthias Fakur's book on causal inference in Python. But it's explaining original ideas that are in this paper from Chernoskov. I have no idea how to pronounce it. I'm sorry if he ever hears it, but it's a beautiful paper about double ML and what's going on in there. So the Frisch-Waugh-Lovall theorem, I will kind of gloss here a little bit, but basically the idea is that for any OLS model, which is trying to predict an outcome Y with a treatment D, for instance, and sort of auxiliary covariates, it could be whatever you want, you can retrieve the beta 1 parameter for the treatment effect in a sort of stepwise manner. So if you first regress the outcome Y on the auxiliary variable Z, Z1 through N, then regress D on the same auxiliary variables. So that's like a propensity score model, right? You're trying to predict your treatment outcome and you're trying to predict your outcome model. Then you can take the residuals from both of these models and fit a regression to the residuals to find the same parameter that you would recover in the more complicated OLS model. So that's maybe an interesting fact about regression, but it's going to get used in an interesting fashion in this double ML kind of framework, because it's tied to the notion that the treatment variable should be, the outcome should be independent of the treatment variable conditional on the covariate profile X. And by setting it up in this way and defining the treatment effect, this beta 1 term, as a function of the residuals of the covariate profiles, Z in this case, but X in the more general case, we have created a variable which by construction cannot be predicted from the covariate profile. So we guarantee independence of X, so to speak. And this is a nice idea that links strong ignorability, i.e. the license for causal inference, to a regression framework in this sense. So we've kind of flagged before at the top that BART models are super flexible. When fit to a particular sample, they can easily sort of explore the outer reaches of the different strata, the different covariate profiles, and fit a propensity score model too accurately, which risks sound inference using those propensity scores in inverse weighting schemes. One way of addressing that without going in and customizing your propensity score model using priors to reweight it is to simply use kind of a k-fold cross-validation technique, where you derive estimates for the propensity scores for a subset of your data, conditional on the other the other parts of your data, so to speak. So what I'm doing here is defining a k-fold, a four-fold in this case, cross-validation split. I'm defining an outcome model. So that is that in this scheme, that is this model. And I'm defining a propensity score model as well. So what we're going to do here is fit both on, so because it's four-fold cross-validation, we're going to have four steps in a loop. At each step, we're going to train the model on 3/4 of the data and score or predict 1/4 of the data to estimate propensity scores for that quarter. And then we're going to stack the 4 predicted propensity scores together to get a better calibrated measure of propensity scores that better reflect the propensity within the population rather than just directly within the sample. Does that make sense? But this is my cross-validate function. So what we're doing is fitting the model, defining the residuals for the outcome, and defining the residuals for the treatment effect. For each quarter of our data, we're doing this in a loop. This takes 8 minutes. I might not run this one, Alex, if that's all right.
Yeah, for sure.
Yeah. So we do that and we stack them so that we get a structure which is like this. So this is effectively a posterior predictive distribution of the Y residuals in the Frisch-Waugh-Lovall framework. And we also have the same for the treatment outcomes residuals. We can then take all of those residuals and fit simple OLS regressions to recover the beta 1 parameter that we specified at the top. So that was a lot of maybe introduction and discussion. The framework is very interesting. I thoroughly recommend Matthias Fakur's book for sort of a deeper dive into these things. But basically what it allows us to do is we now have a sort of posterior distribution of the average treatment effect derived using double ML. And you can kind of see that this is the slope for the residual fits, the last residual fits that we did. And the expected treatment effect is negative 0.02, which is much more in line with our exploratory data analysis. It is a much kind of more sensible result than the one we saw with the raw BART propensity scores. So while we could define a very specific model that avoided the miscalibration of the propensity scores, we can also use this k-fold cross-validation to sort of pull it back to a more sensible view, which is what I think you get here. And it also pulls out a nice estimate of your causal effect. Additionally, in the double ML framework, and again, I'm just going to point people towards the book, but you can use the posterior distribution of the residuals and the propensities that we have pulled out in this double ML process to define a particular kind of target, which is based on that residual, which we can fit with a weighted ML model. I'm going to use random forest here to pull out estimates of the Kate effects. So the conditional average treatment effects, basically per individual covariate profile or per individual, because they're usually unique enough to identify, right? So I'm just going to plot these outcomes here. So across the posterior distribution of our residuals, both the outcome residuals and the treatment residuals, the red distribution here is the Kate distribution for everyone in the control group, and the blue distribution is the Kate distribution for everyone in the treatment group. So what you can, and then on the left and the right, we are plotting the P01 and P99 of the Kate distributions per group. And what is nice to see here is that you can see that the treated groups of the smokers are in the right-hand side of distribution. They're pulling it out further to the right. They have more extreme health expenditure costs in the smoking group than they do in the non-smoker group. Right. So, which is sort of more in line with, yeah, go ahead, Alex.
Yeah, no, I was just saying, just after you finish explaining that, we have a question from Yasser, who wanted to have another explanation for the stacking of the fourfolds in the DML model. And in particular, he's worried about, wondering if that would not result in overfitting rather than evaluating each fold separately.
We are evaluating each fold separately, and then we're stacking them to rebuild our entire data set. So we have like 1,000 observations to begin with. We split it into 4. In this case, we derive for each quarter of the data set. We derive the residuals. And we do for both the treatment and the outcome. We do the process to fit the OLS model on each fold, and we kind of report it out here as well. So the estimated treatment effect on individual fold is 0.001, etc. And then we restack the residuals at the end in this way to recover our 1,000 observations or 4,000 observations. And then we fit an OLS model to all the residuals again. I'm not sure why it would risk overfitting. I think this is doing what it should do.
Thanks, Nathaniel. Sir, tell us if that didn't answer your questions, but I think in the meantime we can keep going.
Okay, yeah. So this is Kate. This is a quantity that you can derive from having fit a double ML type model and gotten the residuals out of it. There are other methods to derive Kate predictions than this, but this is a nice thing to fall out of the double ML framework. The outcomes here, which suggest a kind of more extreme outcomes for the smokers, is, I think, like points to reasons for considering like the heterogeneity of causal impacts in a population. Absolutely. But it's also just more in line with my understanding of what smoking should do to your health. And so I kind of want to kind of remind ourselves that like we've been looking at a data set that no matter which way we cut it, up, down, left or right, propensity scores, regression, or whatever, sort of suggests that smoking has no negative effect on our health expenditure, which should, I think, strike us as strange and ultimately wrong. And I kind of want to say that the solution to this puzzle is not that we've been using poorly specified methods, but we've been asking sort of the wrong question altogether. And it's not that smoking isn't related to healthcare costs, but it's that its impact is mediated through smoking's influence on our health. And there is a causal structure to the nature of this problem that is like, basically this is the structure. So the treatment, which is smoking, it works through a mediator, which in this case is our measures of our health, and affects an outcome in both paths. And what we're seeing, I'm going to argue and try and show, is that the negative effects of smoking are sort of cancelled out by the positive effects of the health statuses of the individuals in our data set. And to sort of disentangle those two quantities, we need to model that correctly. And one way of doing that is to specify a mediation model. Okay, yeah, so that's kind of what I want to say. So let me pull this out here. This is our data set. I'm doing a bit of a transformation here because in our data set, our health statuses are 0-1 variables, like health is poor, health is fair, health is good. I'm restacking them and ranking them to give us an ordinal variable, which is what we're going to use in our mediation model, which you should be able to see. Then I'm going to define a mediation model like this. I can just run this one. All this discussion of mediation and mediation models here, I should stress, I've adapted from a nice PyMC example that Ben Vincent has on the PyMC examples repository. And what I want to show is that this type of model, which was traditionally used a lot in psychology, is a parametric model. So is traditionally a parametric model where you can derive the natural indirect effect and natural direct effect and total effects of this mediation structure that we just saw in the graph using combinations of formula. So using the coefficients derived in the model. I've made a slight tweak to that model in that I'm only specifying coefficients for the intercepts, the treatment variable, and the treatment variable, and the mediator variable, right? But I'm also bundling the rest of the coefficients into a BART model. Sorry, rest of this broad structure. So like seat belts, marital status, race status, all of that gets bundled into a BART structure, right? So this is my effort to kind of compromise our model by giving us enough parameters to recover the traditional Baron-Kenny read-off estimates of natural indirect effect and natural direct effect. And I will also show, using this model, how you can recover similar estimates for these quantities using non-parametric inference, specifically using a type of imputation methodology. Is that clear? I know there's a lot going on in that. So the reason I'm covering that is, so this structure, the model has two likelihoods. It has a likelihood for the mediator. So we are predicting, in a sense, the health outcomes, and we are predicting the cost outcomes, right? Two likelihood terms. Okay, so we can fit this. I'll just fit this now. So what else do I want to say? Yeah, so I'm going to, while that fits, I'm just going to say this model will fit, and then we will be able to read off using the sort of parametric equations that I defined here, these ones, the indirect and total effects and natural indirect effects of smoking on health outcomes. So, and the story you see then is that the direct effect of smoking is negative, so negative 0.85. The indirect effect via the mediator is positive. So the total effect is the sum of these two quantities, which cancels out to 0, which is a better, to my mind, explanation of the data that we saw in this sample than the conclusion that we might derive from fitting these WML processes that there's no effect of smoking on health expenditure. This is a bit slower than I was hoping for, 21%. Let's just let it run as I go and talk about the next thing, because there's a lot. So we have a mediation model. We have a way to read off parametrically the causal estimands of interest, which are the natural effect, natural direct effect, and natural indirect effect, using our mediator and outcome variables in this model. So there is a recipe, I think maybe a recipe is a good way of thinking about it, for taking a fitted model of the mediator and the outcome variable and imputing the results of treatment statuses and combining those imputations to derive estimates for the natural treatment effect and natural indirect effect. And I'm going to show that below. But why that's important is because we could have purely had a mediation model, which was just a BART model. We could have had an outcome model, which was just a Gaussian process model. We don't need to read the parameter estimates off our model at all. We can pursue this recipe to derive the causal estimands of interest, which again, I repeat, are the natural direct effect and the natural indirect effect, using counterfactual imputation, a counterfactual imputation recipe. This is, there's a lot of stuff going on here, but basically what we want here is M is our mediator. It is a potential outcome under different treatment regimes, so T. Y is our outcome variable, which is also a potential outcome variable, but it's kind of a nested potential outcome variable in our causal structure. It's nested in the sense that it is dependent on the realization of the mediating variable, M, right, under different treatment regimes. And so we define in this causal mediation analysis that the natural direct effect is the difference between the outcome variable conditional, the difference between the outcome variable in the treated status versus the non-treated status, conditional on a mediated variable under one of those statuses. Right, so we fix the mediation variable to be non-treated, for instance, and then we push that forward into our assessment of the counterfactual outcomes for the outcome variable under the treated status and under the non-treated status. So I've tried to gloss that here by saying we're interested in the differences in the outcomes under different treatments, mediated by values for the mediator under a specific treatment regime. Right. That's supposed to be the direct effect that we estimate. The indirect effect is different in that we are looking at the differences between the outcome variable under a specific treatment regime, so fixed, while we vary the conditions which generated our mediator. Right? And we get those two quantities out and we sum them and we get the total effect. Okay. I know there's a lot going on here. And this code, I will run through it when the model fits, but I think it needs to be stepped through sort of manually to understand it yourself better. But anyway, our model has fit here, so I will just generate these plots again. So we see here negative 0.79, positive 0.91, and the total effect is 0.0. So they cancel out, which is the nice thing. So how can we recover those parameter estimates by using this counterfactual imputation recipe? So we're going to define a function to generate values, posterior predictive values for our mediator variable, which is the health status, under different treatment regimes, right? We're going to invoke these functions once, right? So this is the inference data object for the mediator under the treatment status where everything is set to 1. Right. And then this is the same idea for the inference data object for a mediator variable, or health outcome, where everything is set to 0.
Yeah. Some questions here. One from Hammer Dirt asking if there are any research papers that you know of that use Bayesian causal inference and propensity scores to identify pollution sources or estimate the cause of changes in biodiversity. So basically any application of what you're showing here, but in the biodiversity climate research realm. And another question from Yasser asking, is the way direct indirect effect derived, is it similar to how the do operator work like in PyMC?
So I know there is a, so maybe actually, so the first question for Hammer Dirt.
Yeah.
Which is amazing. I don't know that literature at all. So I can't really say.
Yeah, me neither.
No idea.
Yeah.
Is the way indirect and direct effect derived similar to how the do operator works, like, for example, in PyMC? So I'm using a potential outcomes framework to express direct and indirect effect. The do operator, which is sort of more beholden to the Judea-Pearl framework of causal inference, has been implemented in PyMC models, and it's sort of a graph mutilation or graph intervention operator. And I know Judea-Pearl has work on how, in his framework, you define indirect and direct effects. Causal mediation is important for him as well, but I don't know his gloss on the literature as well. So I don't know if that answers your question exactly. In code, the do operator in PyMC is just like an intervention on the graph, and you set the variable to be such, and you can push it forward. You can also delete incoming influences on the graph model. So I'm sure you could use it to express the idea of direct and indirect effect, but I'm not doing that here, and I don't know the way in which Pearl would try to express those concepts well enough to comment, if that makes sense.
Yeah, I think so. That depends on the graph, and so do is intervening on the graph, and it's gonna fix a random variable to a value, for instance. So treatment, instead of being a random variable of 0 or 1, is gonna be 1, and then you do posterior predictive sampling on that, and then you do t equals 0, you do posterior predictive on that, and you do the difference, and that's your causal effect. Whether it's direct or indirect is going to be given by the graph, I think, talking very generally. So this is related, and you can do that. You don't have to use do, the do operator, but that definitely helps doing that. But yeah, that's why it's very similar. Yes, sir. It's just like, it's like the idea is the same. Like always when you're trying to compute causal impacts, right? You're trying to compute the difference between a counterfactual and what you observed. And so, like, the question is always, how do you generate the counterfactual? The do operator is one way to do that in PyMC. And when you do that in the Bayesian framework, instead of just having one point estimate, you're going to have full posterior on your causal impact.
Yes. So I think like that's kind of what we're doing here. And the way I've generated these counterfactual inference data objects, which collect that posterior distribution, the posterior predictive distribution, under the different conditions that I've tried to articulate here, will give us. So I'm just doing it for one observation from the posterior distribution of the mediator outcome, right? So of the mediator. So we fit these things and we get a posterior distribution for the entire mediator variable. Right? And what I'm showing here immediately is that we can then define the contrasts which make up the natural indirect and direct effects as differences in the expected likelihood, expected outcome distribution for these counterfactual inference data objects. right? So what you get here in this one case with one posterior draw from the mediator I data is a direct effect of negative 0.8, an indirect effect of positive 9, and a total effect of 0.01, right? And let me just see if I can run all of these to make sure. If I run this one, yeah, I've run that one, so I should be able to run these, which sampled quite quickly because we're only doing one draw. Then we calculate again, we get negative 0.7 in this case, negative 0.9. Okay, well, this is one draw, and then 0.01, right? So still cancelling out broadly. But we've only done one draw from the mediator inference data. So what I'm doing here is I'm going to take 400 draws. Well, I'm not going to do it now because it takes 13 minutes to run. But basically what I'm doing is drawing from the posterior distribution, one sample index from the posterior distribution of the mediator I data, calculating all these quantities again, storing them in a data frame. I jumped ahead. And getting a sort of posterior distribution of the natural indirect effect and natural direct effect conditional on the posterior predictive distribution for the mediator. I only got 400 draws here just because it takes a long time. I'm sure there's a more efficient way of doing this kind of stepwise impute the mediator, impute the outcome, combine them. But this is a way that just worked. I'd need to think about it a bit more if I can think of a more efficient way to do this. But I think this is enough to show the technique, to show that we can kind of recover estimates for the natural direct effect, natural indirect effect, and the total effect. And yeah, so maybe I will jump to my slides because I think we're basically at the end. And I have a conclusion somewhere. Let's see. Yeah. Okay, can you see my slides now again? Go to code, Act 3. So yeah, so in Act 3, we want to talk about causal structure, mediation, non-parametric estimation of the mediation, or the causal estimands under mediation, and the sort of escalating structural assumptions and Bayesian inference that we've seen throughout this entire notebook. This is the parametric mediation kind of formulas that you saw, and these are the non-parametric estimation routines that we saw as well. So the conclusion I kind of want to draw out here is that what we have seen in all cases so far, is that the methodologies are characterized more or less by beliefs and the commitments or assumptions about the data generating process in some sense. So the propensity score adjustment methodology, pursuing it, reflects a belief in the need for the adjustment. Right? It reflects beliefs about the structure of your data set that you need adjustment for. It reflects a belief in the adequacy of the propensity score model for achieving that balance. That's a structural commitment. It's an assumption. It's a belief about your model. Regression-based imputation of treatment effects reflects a belief that the covariate controls that you've selected in your regression model are enough to eliminate the selection effects that we worry about when we're facing observed data. Doubly robust methods are interesting because they reflect the belief that one or two models that you have in your head are correct. It's either the outcome model or the propensity model, and one of them ought to be adequately specified. That's the closest I can get to sort of like truly agnostic statistics. You're withholding belief between which one you think is right, and you are committing that at least one of them is, but not specifying which is a weird way to think about things. Debiased ML methods reflect the belief that misspecification can be corrected by cross-validation and non-parametric estimation of residuals in the FWL theorem. That's in the Frisch-Waugh-Lovall theorem. Mediation analysis, probably the most assumptions we've made is in mediation analysis, reflects the belief that the causal influence must be interpreted with a particular causal structure to avoid confounding. But in all of these cases, inference proceeds by taking steps to adjust our model or the conditions of its assessment, which is informed by our best beliefs regarding the problem to hand. So like there aren't no truly agnostic statistics. There are just varying degrees of beliefs that underwrite the methodologies you pursue. And I think if you're going to model these things that require such commitments, you should always be Bayesian about it. But that's just propaganda. Anyway, that's my conclusion. And thank you for listening.
Awesome. Thanks a lot. Thanks a lot, Nathaniel. That was really super cool. I'm impressed that you were able to go through the whole notebook and the slides in less than 2 hours. Well done. I mean, that I know that must have been exhausting, so we're not gonna take too much of your time now. Let me check if there are some last questions. No, mainly a lot of thank yous, because that was really awesome. So thank you so much for taking the time. Of course, I particularly appreciated the conclusion. So yeah, that was really awesome, Nathaniel. Thanks a lot for taking the time. Oh yeah, will the slides be available somewhere?
Yeah, they're online. I just shared the link there, so it's on my website. That's the link there.
Yeah. Okay. Perfect. Yeah. And anyways, all the links, so to the notebook and to the slides mainly, are going to be available on YouTube for the people who want to dig deeper. The recording is going to be available as soon as possible for the patrons of the show, and then it's going to be available 1 month later for everybody else. And I think that's all. If you want to support the show and become a patron, then just go to LearnBasedStats. To patreon.com/LearnBasedStats. If you want to follow the show, just go to LearnBasedStats.com. Also, all the links to Nathaniel website, socials, and so on, if you want to follow his work, are going to be in the description of YouTube. And I think that's all for now. Any closing thoughts, Nathaniel? Anything I missed?
No, I don't think so. Thank you for listening. Yeah, I think there's a lot there in the notebook already. If I haven't covered it, I do encourage people to read it. The material behind it, definitely look into some of the books referenced there. They're deep and I think very profound in some cases. So,
yeah, for sure. Give a read to the full notebook because it's really dense. Lots of info. I really recommend looking into that, like reading it, because you're gonna learn a lot. And Nathaniel did an awesome job today going through that. But you're gonna get even more by, well, probably going back to the recording and reading the notebook at the same time. I think that's gonna be perfect. Awesome. Well, thanks a lot, Nathaniel, again, and thank you everybody for joining. You were a lot, very engaged, so that was really cool. I had a blast, and I hope you did too. And well, follow the show on YouTube or Twitter or whatever, or on LinkedIn if you wanna know when the next webinar will be. It will very probably be in April. With Juan Orduz, and we are going to talk about Gaussian processes, and in particular Hilbert space Gaussian processes, so a new decomposition of Gaussian processes, which make it actually able to sample, so that's pretty cool. So I'm working on that these days with Bill Engels and Juan Orduz. Hopefully we'll bring that to you at the beginning of April. And if you have any suggestions for coming webinars, well, get in touch. And on that note, see you very soon. And, well, best Bayesian wishes.
Let me show you how to be a good Bayesian.